All right, let's go ahead and get started. I do want to welcome you back to this second screencast of Unit 5. This is bonding. We've taken a look at three types of bonds now. We've taken a look at ionic bonding, in which it was a transfer of electrons from one atom to another atom. We've taken a look at covalently bonded compounds, in which there was a sharing of electrons. If it was an equal sharing, we call that nonpolar covalent. If it was an unequal sharing, we call that polar covalent. And then finally, we looked at metallic bonding, in which there was a sea of electrons, and that sea of electrons allowed metals to conduct heat and electricity readily. But how do we predict whether a molecule or whether something is going to be ionic, covalent, or metallic? Well, let's take a look at a couple of examples. Let's take a look at magnesium chloride, or MgCl2. Well, to answer the question of whether or not or how magnesium chloride is going to form, if it's going to be ionic, covalent, or metallic, we're going to have to know where the elements are coming from on the periodic table. So let's find magnesium on the periodic table. It's on the left side of the periodic table, to the extreme left side of the zigzag line. Chlorine, on the other hand, is on the opposite end of the periodic table. It's on the other side of the periodic table. So that means that magnesium is going to give up electrons to chlorine. This is going to be an ionic bond. Remember, anytime that you have a metal with a nonmetal, something from the left with something from the right, you don't even have to do the electronegativity calculation to determine whether it's above 1.7 or not. It doesn't matter. The point is that it's a metal with a nonmetal, it's going to be ionic. There's going to be a transfer of electrons, not a sharing of electrons. But let's take a look at CO2, carbon dioxide. So now the two atoms that are involved are carbon and oxygen. Where are they on the periodic table? Well, they're both to the right of the zigzag line, right? They're both on the right-hand side of that zigzag line, and that means they're both nonmetals. What type of bonds are formed when you have two nonmetals? Covalent bonds, right? The electronegativity difference is not above 1.7. You're not going to have a big enough electronegativity to form an ionic bond. It's going to be covalent, right? And because the atoms are not the same exactly, by the way, one's carbon, one's oxygen, it's going to be a polar covalent bond. In fact, we'll go one step further and say that oxygen, because it's farther on the periodic table up and to the right, is more electronegative than as carbon, and therefore it's a polar covalent bond, with the electronegativity being greater for oxygen than for carbon. What type of compound is water? Well, I neglected to tell you this before, but water is a little trickier. Actually, hydrogen is a little tricky, because the rule that I've been using is if it's on the left and it's on the right, it's ionic. But actually, hydrogen is an exception. So let's bear in mind, hydrogen always, anytime hydrogen is involved in a bond, it's going to be covalent. Now, we're going to need to remember that. Anytime hydrogen is involved in a bond, it's going to be covalent. Even though hydrogen is on the left-hand side, it's going to be covalent. And then let's take this last one. What type of compound is lithium bromide, LiBr? Well, lithium's on the left, bromine's on the right. That's going to be ionic. So let's review that. If one's from the left, one's from the right, ionic. If both are from the right, covalent. If both are from the left, that's going to be metallic, and that's going to involve that sea of electrons that we talked about earlier. So let's get a little bit more bonding practice. Let's take a look at this diagram. We can see that it's very symmetrical, right? What you see on the left is the same as what you see on the right. So I'll just draw kind of a dotted line right through there. It says the bond shown above is a non-polar covalent bond. Non-polar meaning symmetrical. This bond is between two atoms which are identical. I don't know what they are. Maybe they're chlorine and chlorine, or hydrogen and hydrogen. It really doesn't matter. The point is they have the same electronegativities. Now, the type of bonding can also be determined by calculating the differences in electronegativities, as we mentioned before. For example, fluorine, we've already known it has an electronegativity of 4.0. And by the way, there's no need for you to memorize all the electronegativities, obviously. All I want you to remember is that the big number, the highest electronegativity, is 4.0. So 4.0 for fluorine. Boron has an electronegativity of 2.0. So if boron and fluorine are going to come together in a bond, the electronegativity difference between boron and fluorine is going to be, well, 4.0 minus 2.0, 2.0. Since this number is bigger than 1.7, boron and fluorine, if they bond, are going to form an ionic bond. Now, what if we have two identical atoms? Say, for example, if we have fluorine and fluorine, or chlorine and chlorine, whatever the case may be, the electronegativity difference is 0. It's 0. Since this value is less than 0.3, obviously, this is a nonpolar covalent bond. It's also known as a pure covalent bond. So pure and nonpolar mean the same thing. Okay? So let's review. Electronegativity differences between 0.3 and 1.7 are considered polar covalent bonds. All right? Let's go through all of them. So if we have anywhere between 0 and 0.3, 0 and 0.3, we call that non-polar covalent. Non-polar covalent. Anything between 0.3 and 1.7 is going to be polar covalent. So if that electronegativity is between those two, polar covalent, and anything above 1.7 is going to be ionic. So there you have it. One more time, 0 to 0.3 nonpolar covalent, 0.3 to 1.7 polar covalent, anything above 1.7 ionic. All right, let's go back to the octet rule. Remember, the octet rule states that chemical compounds tend to form so that each of the atoms, by gaining, losing, or sharing electrons, has an octet of electrons in its highest occupied energy level. So the octet rule is really what is driving chemical bonding, right? It's really what's bonding chemical bonding. Everything's trying to get to 8 electrons, with one exception, as we'll look at in just a moment, and that is hydrogen. Hydrogen actually needs only 2 electrons around it, not the normal 8. So the question is to use the octet rule to explain why fluorine is diatomic and why hydrogen and chlorine form hydrogen chloride. So let's start with the fluorine. So let's find fluorine on the periodic table. Well, it's a halogen. It has 7 valence electrons, right? 7 valence electrons. So fluorine is 1, 2, 3, 4, 5, 6, 7. We'll talk a lot more about Lewis structures later, but that's how we draw the electron arrangement around atoms. We pair the electrons up, right? Just like I've done, until you can't anymore, right? So in this case, there were 7. That's an odd number. So it's 1, 2, 3, 4, 5, 6, 7 electrons around the fluorine. Now imagine a fluorine floating around in the universe. What might it encounter? Well, it might encounter another fluorine. So if fluorine encounters another fluorine, it can make a deal. Now I'm going to draw the electrons of this fluorine a little bit differently. I'm going to make them little X's just like that. There's 1, 2, 3, 4, 5, 6, 7 electrons for that fluorine. Now look what happens in this arrangement. The fluorine on the left feels as though it has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. And it feels this even though it only brought 7 electrons to the bond. And the fluorine on the right feels as though it has 1, 2, 3, 4, 5, 6, 7 electrons, with an 8th electron being contributed by the atom on the left. So it feels as though it has 8 electrons as well. So it's a win-win situation for both fluorines, right? Both feel as though they have 8 electrons surrounding them. Now what about hydrogen chloride? Why would that form a covalent bond? Well, remember, hydrogen has 1 valence electron and chlorine has 7. Again, I'll use little X's this time for those 7. 1, 2, 3, 4, 5, 6, 7. Now look at the hydrogen on the left. It feels as though it has 2 electrons surrounding it. Now those 2 electrons are all hydrogen needs to be happy. Chlorine needs 8, and it feels as though it has 8. The 7 that it contributed plus one more from the hydrogen. So both of these are covalently bonded compounds. In both of these, there's a sharing of electrons, okay? All right, now I've already introduced this concept of electron dot or Lewis notation in illustrating these, but I want to do it in a more formal way. What do we mean by electron dot or Lewis notation? Well, it's an electron configuration notation in which the only valence electrons of an atom of a particular element are shown. So we're only concerned about outer shell electrons, right? Let's take a look at chlorine. Chlorine is in the 7th column, or I should say, I'm sorry, the 17th column. It has 7 valence electrons around it, right? 7 valence electrons around it. So here they are, and we've already said that the way we draw them is we pair them up, 1, 2, 3, 4, 5, 6, until we no longer can pair them. So that's the valence or electron dot notation for chlorine. Now you might say, well, why did you put the lone electron on the bottom? Well, you could have put it on the top, on the left, or the right. It really doesn't matter. The point is you're going to have 7 valence electrons, right? So that's just an introduction then to electron dot notation. We'll talk a lot more about that later. Now, let's talk a little bit about the electron dot notations for the following elements, all right? Tell you what, let's do this. Let's take a break here, and I think this is a good stopping place. We'll look on the next screencast at how to do electron dot notations. You might want to attempt these on your own by looking at, before we get there, by looking at the periodic table to find where they land on the periodic table, and from that, determining the number of valence electrons. Folks, I'll see you in the next one. Thanks. Bye-bye.